Hi again, calculus students, and thanks for tuning in. This week we continue on with derivative tests, and we're talking about the second derivative test today. So basically what this test does is uses the second derivative. And so we're going to look at what does the second derivative even tell us about our function, and then see how that could maybe help us test to see if we have relative extrema as well. So let's get right to it. Before we begin with the second derivative, we have to define something, a new concept for you, and it's called concavity. And it's talking about curvature, basically, of a function. And let me draw a function first of all, and we'll talk about some concavity that it will have, and then we'll get some a little bit more formal definition of what we mean by concavity here, just as soon as we get this part taken care of. So I'm going to draw a function that if you've been in my class for a while, you're used to seeing it. Something that looks like this. Oh, maybe let's make it a little more curvy. There we go. And so the idea in the concavity discussion is looking at where is it concave up and where is it concave down. And by concave up, we mean curving up like a cup. Yeah, up like a cup. This area right here. And it would actually probably continue to curve up like a cup if we went up this direction. So that would all be concave up. And over here on the other side, well, we have concave down like a frown. So yeah, down like a frown right here. So here's concave down, and over here is concave up. So graphically, that's what it's going to look like. And you could probably think that this is like a third degree polynomial or something like that, where it's curving, down for part of it. And then there's a point where it switches, and then it goes concave up for a while. If you think about a sine wave or a cosine wave, there's lots of places, right, where it's concave down, concave up. And so, depending on the function you're looking at, you could have multiple intervals which is concave up or concave down. I just want to get the idea, first of all, about concave up and concave down. Now, the interesting thing about this is we actually need to define it in terms of calculus, right? I could always have I could describe up and down concavity to an algebra student or a pre-calculus student, and they would have a pretty good understanding, and they could probably isolate that where it's up and down and pretty easily. So what does calculus have to say on the matter? Well, what I would like to consider is, what is the first derivative doing in each of these sections? Okay, and so by that I mean, let me get back to my original graph here. If I imagine the tangent line, okay, so like over here, I have a tangent line like so. Okay, but if I move closer, if I continue to move across, oops, come on, grab that line. That doesn't really work as the tangent line over here, right? I'd have to adjust the slope, right? And as I get closer and closer to that relative extrema there, what happens is the tangent line is getting closer and closer to zero. And as soon as I get past that relative extrema, just like we saw with the first derivative test, right? That's the change in sign of the first derivative. Now all of a sudden, my first derivative, tangent line slope, is negative. And it's going to get more negative as I continue to move to the right, right? There's a steeper negative slope here as we continue to move across. So what happened to the first derivative? The first derivative started out being positive until we hit that relative max, and then it turned negative. But notice it was positive, but it was getting less and less steep. In other words, the first derivative was decreasing. And that's how we define concave down. Concave down is literally defined as an interval where the first derivative is decreasing. Okay, so let's write that down. Concave down, an interval where f prime of x is decreasing. Okay, So it's okay that it starts out positive, it just turns into decreasing, right? Well, as you can probably guess then, what happens for concave up? Well, continuing on, okay, if I continue to move this tangent line across here, as I get closer to this relative min, of course, now what has to happen? Well, you can see, yeah, the slope of the tangent line, that first derivative, is getting bigger, right? It's getting less negative, which is increasing, right? And then as soon as we get past that relative min there, right here, right, my first derivative is going to start getting positive again. And so sure enough, just as you probably already figured it out, that concave up is an interval, an interval where f prime of x is increasing. Now, what I want you to consider for a second is if f prime, just think of f prime as its own function then, okay, how would you know it was increasing or decreasing, okay, using calculus, right? If I think f prime is decreasing, it's going down, so its derivative must be negative, right? Well, the derivative of the first derivative is, of course, the second derivative. That means, oh, I didn't mean to do that. Sorry. Ah, uh-oh. There we go. Let's turn that, let's turn that text blue again. I didn't mean to do that. There we go. Because what I'm getting at here, guys, is that f double prime of x, the second derivative of x, is negative. Okay, that's what, if f prime of x is decreasing, its derivative must be negative, right? We saw that in the first derivative stuff, right? A function was decreasing when its derivative was negative. Well, we're just talking about f prime as if it were its own function. And sure enough, guess what? An interval where f prime is increasing, okay, means its derivative is positive, which is f double prime is positive. So we actually can describe concavity by looking at the sign of the second derivative. And that's where we begin today, is looking at the second derivative and looking at what it tells us about the concavity of our function. Okay, now you may be wondering, well, what happens at that point where it changes, right? There is a point on my graph over here, right here, where we have a change in concavity. It was negative, and then it's positive. Well, if this is a nice continuous function, then its derivative exists everywhere. And because this was a polynomial, we know its derivative is a polynomial, which is also continuous and differentiable anywhere. Well, the intermediate value theorem tells us we can't go from negative to positive without going through zero. So the point here is called an inflection point. And inflection points are where the second derivative is zero and there's a change in sign of the second derivative. Now, so it's kind of like critical numbers, okay? It's like trying to find critical numbers from the first derivative. I don't want to call them critical numbers because they're not. Critical numbers are defined to be where the first derivative is zero or undefined. Okay, but when we're looking for an inflection point, then what we're going to be looking for is that point where the second derivative is zero. Okay, and similar to critical numbers, it's also where the second derivative maybe is undefined. So that's what an inflection point is, but there has to be that change in sign in the concavity, okay, in the second derivative for us to have what we call an inflection point. So rather than calling them critical numbers, we sometimes call them the possible points of inflection, or PPI is the acronym we came up with last year. And so we will consider looking for PPI, possible points of inflection, like in the first derivative, only in the second derivative, we're looking for where it's 0 or undefined. We will make the same kind of sign chart. Okay, so I will make a sign chart and I will look at what the sign of the second derivative is doing on either side of one of my PPI. So let's take a look at a function so that we can determine if we have some points of inflection, and we can look at some concavity. And the function I have here, let's write this one out. This is f of x. And I'm going to start us off with a nice, fairly straightforward polynomial, just because we like polynomials because they're continuous and differential everywhere. And so makes life nice and easy. So here is x to the fourth plus or minus 4x cubed, and that's the one we're going to start with. So let's begin by finding our first derivative, but this time we're going to just continue right past that first derivative and continue on into our second derivative. So f prime of x, just using some power rule here, bring down my power, subtract 1 from the power, like so. And then let's just go straight to the second derivative. So let's try that again. So f double prime of x would be 12x squared minus 24x. And right there, we see, because it's a polynomial, we knew the first derivative was going to be continuous and differentiable, because, polynomials are well behaved, and second derivative, that's continuous everywhere, differentiable everywhere. So, we've got nice, well behaved functions here. Okay. I want to find those PPIs, those possible points of inflection, because that's how I'm going to set up my sign chart for my second derivative. So you may notice that this is nice and factorable. Oops, I'm not too excited there. I'm writing my numbers down. I can factor out the 12x, right? And so 12x times x minus 2. And so we end up with two possible points of inflection. We've got 0 and positive 2. And so those are the ones I'm going to use to make my sign chart. And so let me make my sign chart here. Let's get a chart drawn over here. And let's make a little, let's see here. We got to go with like -1, 0, 1, 2, 3. And I'll mark off my possible points of inflection here at 0. And don't worry, I'll move these around here. Oops, I put that on the wrong one. So yeah, it's hard to get them in the right spot when you're drawing freehand on this. There we go. Oh, come on. Oh, just stand still. There we go. And so now let's take a look at what are the signs of f double prime doing for these values of x. So nicely labeled. Here we go. And I'm just going to go back to my second derivative and say, well, okay, if I put in -1, okay, if I'm looking at f double prime of -1, I get 12 times -1 times -1 minus 2. Okay, and notice 12 times -1 would be a negative number. -1 minus -2, that'd be a negative number. So negative times negative, we get positive. And really, again, all we're concerned about is what is the sign of the second derivative over there. So I know from -infinity to 0, it's concave up like a cup because it's got a positive second derivative. The first derivative is increasing on that interval. Okay, what's happening between 0 and 2? Well, let's find f double prime of +1. Well, you get 12 positive times 1 positive times 1 minus 2 negative. Aha. We have concave down on the interval 0 to 2. And finally, test point at 3, I get 12 positive, 3 positive, 3 minus 2 positive, 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 concave up again. And so I have established that I have 2 points of inflection. I have a point of inflection at x equals 0. I also have a point of inflection at x equals 2. Now, I want to be careful with my language here, because if I say that I have a point of inflection, remember that points on the Cartesian coordinate system require 2 coordinates, okay, an x and a y. So if they ask for points of inflection, guys, make sure you give them an X and a Y coordinate. Okay, so I have a point of inflection at, well, 0, 0. That looks like a nose. Hold on, get that out of there. Let's put a comma in there. There we go. And why is that? Well, the nice thing is because F double prime changes sign. We're not justifying like a relative min or max. Okay, we're just saying point of inflection. So all we need is a sign change. We don't care if it's positive, negative, negative to positive. Similarly, if you were to plug in the point 2, you would get negative 18, and that would be the other point, 2 comma negative 18. Similarly, because F double prime changes sign. So that's what our information that we've got from our second derivative tells us. Let's take a look at the actual graph of the function. I have it graphed from earlier. Let me go over to Desmos here. And here's what I have. And let me grab my annotation tool here. Sorry, it's on the other screen. Bring that over. And notice, oh yeah, let's turn that off. I'm already in annotation. Okay. There we go. Just exactly what we said was going to happen is happening here on this graph. Okay. Over here, from negative infinity to 0, right? See, we have concave up. There's that inflection point. Now it's a little tough to see, but oh, maybe it's 2 negative 15. I didn't actually plug it in. I was just trying to read it off the graph. It's hard to see exactly because we have this huge, deep dive to this relative min is way down here at negative 27. So I think I said negative 18. It looks pretty close to negative 18, whatever that value is in there. I was thinking maybe I should have said negative 15. Let's see. I didn't actually compute it earlier. I was just trying to read a graph. What was it? It was 2, right? 2 to the 4th minus 4 times 2 to the 3rd. Negative 16. Oh, yeah, well, sorry, guys. We're not going to go back and redo this part of the video for that. We're just going to put it right there at negative 16. My apologies for misreading my graph. I was trying to read the one out of the textbook, so I missed it. But notice we do have a nice concave down sort of feature all the way down through here. And then after negative 16 is concave up the rest of the way. So exactly what we said was going to happen. We have our positive second derivative. Then from here to here, we have our negative second derivative. And then from 2 on to infinity, we have our positive second derivative. Yeah, so it turns out, we have a nice match with exactly what we got on our graph. Okay, let me clear these annotations. I want to talk to you a minute now about the actual second derivative test, because what the second derivative test is for finding relative extrema. Okay, and I want you to notice that down here at, oh, gotta grab my pen again. There we go. Down here at 4, negative 27, okay, we have a relative minimum. Okay, now we know it's a relative minimum because we can see it on the graph. Okay, could we have been able to figure that out using the fact that 4 must be a critical number? Okay, because it's got to be a critical number because relative extrema only happen at critical numbers, and we'll go back to the algebra in a second and show that it's a critical number. And the fact that it's concave up. Okay, because if you think about it, if we have a critical number, then the slope of the tangent line is horizontal. Is there any way to have concave up at a point with a 0 slope tangent line and not be a relative min? If I'm drawing any graph, steep graph, whatever, it's impossible for us to do that, and it still have it be a without it being a relative min. So when we go back to our algebra here, okay, let me move that over to the main screen here. Oh, that's not going to work. I'm gonna have to work on the other side of the screen. Sorry, guys. I want you to examine that first derivative for me for a quick second. So let's just take this guy. Oops, that's not what I meant to do. This is what I meant to do. This guy right here. And just real quickly factor that. Okay. So this is f prime of x. Well, you take out the 4x squared, and what do you get? X minus 3. Okay. Well, I think I said 4 when we were looking at the graph, but you knew I meant 3. And so I have two critical numbers. Now, these are real critical numbers because we're looking at the first derivative now, right? My two critical numbers are 0 and 3. And notice at 3, we have concave up. Okay, there is no way, excuse me, to have a graph concave up with a 0 derivative, 0 first derivative, and not have it be a relative min. Similarly, you cannot have concave down and a 0 derivative and have it be anything other than a relative max. That's what the second derivative test is all about. It's on page 188 in your book. It's theorem 3.9. It's the second derivative test. It basically says, hey, look, take your critical numbers from your first derivative, plug them into the second derivative, and see if it's concave up or concave down at that point. And if it's concave up, great, it's a relative min. If it's concave down, it's a relative max. Okay. Notice we got another one here. We had 0. That's a critical number. Okay. But what happened when we put it into the second derivative? We got 0 there as well. So not a critical number. I'm sorry, it is a critical number. It's not a relative extrema. Turns out that that was an inflection point. Okay, so what does it mean? Well, if we go back and look at the graph, it means that there is a small, brief, instantaneous moment where at 0, the slope is exactly 0, okay, but there's no change in sign of the first derivative. See, the first derivative would be negative. I lost my annotation tablet again, darn it. There we go. I'd still have a 0 first derivative here, but notice all my slopes are negative on either side. So there's no change in sign in the first derivative. That's just an inflection point. Okay, that's why we have to test them. Okay, and that's why we have to test them in the first derivative or with the second derivative. But you are able to see that that is actually just a spot where it flattened out just momentarily, but is in fact not really a relative extrema. So that is the second derivative test. Again, check out page 188. It shows you the actual second derivative test. It tells you just exactly what we were just saying, that if you are looking at your critical numbers from your first derivative, okay, for the critical numbers, use your critical numbers. And then say, well, if f double prime of c is positive, then f of c is a relative min. Okay. If f double prime of c is negative, then f of c is a relative max. It does also, there is one possibility. If f double prime of c is 0, the test fails. Go back to the first derivative test. Okay. Yeah, if it does turn out that f double prime of one of your critical numbers is in fact 0, and you're looking for relative extrema, you're going to have to go back to the first derivative test. Now, like we saw in our example, okay, it turned out f double prime of 0 was also 0. So if I was using the second derivative test to justify relative extrema, I would say, oh, the test failed, I'll go back to the first derivative test. We didn't really need to do that because we could prove quite easily that that was actually an inflection point. So it wouldn't be a critical number. So, all right, thank you guys so much. If you have questions, don't worry, we have plenty of time to go over this in class when I see you guys on Friday. So thanks so much for watching, and I'll see you guys in class.